So we're going to move on from Maclaurin series and we're going to look at Taylor series this time. And remember, Taylor series are essentially Maclaurin series, except that we're not centered about zero anymore. We're centered about some other point A. All right. And so we're going to do the exact same thing that we did before. So we're going to start by finding successive derivatives. We're going to substitute them back into this form to be able to find the Taylor series. And then we're going to be able to hopefully find some sort of summation notation. All right, so let's start off with a function f of x is equal to 2 ln of x. All right, and remember, we start with n, and we have 0, 1, 2, 3. Now we're hoping that all these terms are non-zero, but if they're not, then we'll just go through and fix that. Okay, and then we're going to find the nth derivative. And then this time, we're not going to find the nth derivative at 0. Since a is equal to 1, we're going to find the nth derivative at 1. Now remember, the 0th derivative is always the original function. And when we substitute 1 back in, this is going to be 2 ln of 1, which is equal to 0. So we know that we're going to need at least a 4th derivative for this. But that's okay. It won't be that bad. First derivative is going to be 2 over x, or 2x to the minus 1. And when we substitute 1 back in, that just gives us 2. All right, so we're going to hold on to that. Next derivative is going to be negative 2x to the minus 2. And so that'll be negative 2 times 1 to the minus 2, which is negative 2. For the next one, we're going to have positive 4, and that's going to be x to the minus 3. All right, and then in other words, that's going to simplify into 4 times 1 to the minus 3, which is going to be equal to 4. And then finally, for the last one that we have, this is going to be negative 12 x to the minus 4. And this is going to be negative 12 times 1 to the minus 4th, which is going to be negative 12. All right, so when we write the closed form for our Taylor series, or at least the first 4 terms to get to our closed form, we're going to call this, so we have a 0, and then we have our 2 here, and usually we write 2x, all right, but what we're going to do is we're going to say x minus 1. Okay, so remember, that's because we're centering about a equals 1, and so we have the derivative evaluated at a, which was 1, and then x minus 1. And the same thing here, second derivative 1, x minus 1 squared divided by 2. So this is going to be minus 2 over 2 factorial x minus 1 squared plus 4 over 3 factorial, and that's going to be x minus 1 to the 3rd. And then finally, minus 12 over 4 factorial, and that's going to be x minus 1 to the 4th power. All right, so these are the first non-zero 4 terms, the first 4 non-zero terms of this polynomial 2 ln of x, or this Taylor series. All right, now we have to guess some sort of summation notation for this, and that's where we look for our patterns. All right, so we always want to look for patterns when we're doing these things. All right, so one thing that we could do is we might be able to simplify each of the expressions and maybe find like some sort of like power of 2 or something like that. All right, that might get us to whatever we want with this. All right, so we notice that right here we have like a 2. All right, and so if we go through and we just simplify this, all right, into some sort of like summation notation for part B. Now we know that this guy right here, we can write this as 12 over 4 times 3 times 2 times 1, or in other words, that's going to be 2 over 4 if we wanted to simplify that, all right, or a half if we really wanted to. Over here, we could write this as 4 over 3 times 2 times 1, which would be 2 over 3. And then over here, this would be 2 over 2, and this would be 2 over 1 if we really wanted to write this. So it looks like that each of the powers in the denominator is just going to be the same as the power that's affixed to each of the exponents, okay? And there's always going to be like this other 2 in the numerator, okay? That 2 is actually coming from right here because we had 2 ln of x, all right? So if I were to go through and write a series for this, all right, so we would have the series of n equals 1 to infinity, all right, because remember, the 0th term did not contribute, so we're not going to count that. We're going to have the 2. We're going to have x minus 1 to the nth power, all right, so notice here we have like a first, second, third, okay? And then over here, when we simplified, we had a 1, a 2, a 3, and a 4. So that was the same thing as n. So we're going to divide that by n. All right. And that's about as good as we're going to get with this, except for the alternating component. Okay. So notice we have positive, negative, positive, negative. All right. So I'm going to start this with minus 1 to the n. And let's see what happens when n equals 1 and then n equals 2. Right? So if n equals 1, this becomes minus 1 to the first, which is negative 1, and that doesn't match the first sign. And then if we have minus 1 to the 2, that's going to be a positive 1, which doesn't match the second sign. Okay, so this doesn't work. So if it's not minus 1 to the n, I'm going to factor the 2 out. So we have 2 series n equals 1 to infinity, x minus 1 to the n divided by n. And we're going to make this minus 1 to the n plus 1. All right, so it's either n or n plus 1 for your exponent. Okay, so this is going to be our exponent. All right, so that's the way to check which of the alternating factors you're going to use. All right, so just start the lowest power or the lowest bound of your index and just substitute in. All right, so we're going to take a look at one more Maclaurin series in the next video, and then we're finally going to see an example of where we're going to use that Maclaurin series. Oh, sorry, one more Taylor series, excuse me. And then we're going to take a look at where we're going to use our Taylor series in the final video.